to our machine design series. Today we are going to talk about gear trains. And to start us off, I have a drawing down here of what a gear train might look like. All right, so first, let's just have a note on nomenclature. So the number 1 will be reserved for the frame that holds all these gears in place. And then number 2 will be the input gear, and we number all the subsequent gears after that, 3, 4, 5, 6. And we will also use lowercase letters for each of the shafts. So shaft A will be on the input gear, then shaft B, here's shaft C, which extends all the way through gear 5, and then shaft D on the end there. Now I can also draw this gear train from a side view, and you might see this. So you may just see some circles like this. Okay, this is a perfectly good drawing representing the same system as above. And in this gear train, we have a pinion, which is gear number 2. Remember, the pinion is the smaller of 2 gears that are meshed together. This pinion 2 is driving gear 3. And if we know the direction of our input gear, then we can work out what the direction of the output gear is. So let's say that gear 2 is rotating clockwise with a speed n2. Then we know that gear 3 has to be rotating counterclockwise, right? Because when these teeth mesh together, the speed of those teeth is going to be going in one direction, down this way. And so that means that the third gear has to have a flipped direction of rotation as compared to the first gear. Okay, and the same thing is true for gear number 4. It's going to have to be going clockwise, flip direction from gear 3. And now gears 4 and 5, you can see they're on the same shaft. And so if gear 4 is rotating clockwise, then gear 5 will also rotate clockwise. They're not meshed together, gears 4 and 5. They're just on the same shaft. And speeds 4 and 5, their angular speeds are going to be the same. They're just going to be whatever speed that shaft is rotating. And then lastly, we have gear 6, and that one is going to rotate counterclockwise. All right, so we have this relationship where we can work out the speed of the rotational speed or angular velocity of a gear that is in mesh with another gear if we know the number of teeth on both gears and we know the speed of one of the gears. And that's through this ratio of the number of teeth on each gear or the pitch diameter of each gear. And this just comes from the fact that the pitch line velocities at the interface between the teeth, we have to have the same pitch line velocity at this interface, and it's going to be the speed of gear 2 times the radius of gear 2, or the speed of gear 3 times the radius of gear 3. So if we just rearrange that equation, that relationship a little bit, we can get this bottom form of the equation. And then if we just use the fact that both of these gears have to have the same diametral pitch because they're meshed together, so they have to have similar gear teeth sizes and spacing, then we can use the relationship between diametral pitch and number of teeth and pitch diameter to get the top form of this equation. Okay, so that's where all that comes from. Now, if we want to get the speed of the output gear from the speed of the input gear without going through this process, 6 times, we can go ahead and write the speed of that output gear just using the ratios of the number of teeth from 2 to 3, 3 to 4. So let me write out what that looks like. Okay, now let's talk about this equation. So first of all, you'll notice that I put a negative sign out in front, and that is just to indicate that the input gear, gear 2, is rotating clockwise, and the output gear, gear 6, is rotating counterclockwise. So we're flipping direction. And next, we have the ratios of the number of teeth on 2 to 3, 3 to 4, that's this ratio. And then we skip 4 to 5, and we just go on to the ratio between 5 and 6. And that is because 4 and 5 are not meshed together. They're just on the same shaft. So the teeth are not interfacing between gears 4 and 5. They're just rotating at the same speed. And so we don't need to do this conversion where we use the fact that the pitch line velocities of the teeth are moving at the same speed, because they're not. The angular velocity of the two is just the same. N4 is just equal to N5. So one more thing to notice about this equation is that if I simplify it, the number of teeth on gear 3 is going to cancel out of this equation, right? It's on top and bottom. And that indicates that gear 3 is an idler gear. What that means is that it does not have an effect on the change in speed from the input to the output velocity. The only thing that this idler gear is doing is it is reversing the direction. So without this idler gear, the speed of gear 6 in this equation, we would have a positive number right here, and gear 6 would be rotating clockwise if we didn't have gear 3 in this gear train. Okay, so now let's write a more general form of this equation we've written for the speed of the output gear. Alright, so here's an equation for the train value of a gear train, which you may have also heard people call a gear ratio. It is a number that tells us the change in the speed of the output gear from the speed of the input gear. 1 over the train value will also tell you the change in the output torque from the input torque. So if we look at our equation that we've written up here, this area that I'm boxing that is just the ratios of the gear teeth, that is the train value for this gear set that is up here. So if you look at how this equation is written, we're looking at the product of driving tooth numbers on the numerator. So gear 2 is driving gear 3, gear 3 is driving gear 4, and gear 5 is driving gear 6. So we have the number of teeth on 2, 3, and 5, and then number 3 is being driven, number 4 is being driven, and number 6 is being driven. Now, a couple of tricks on how to figure out the sign. So this train value is going to be positive, of course, if the first and last gears rotate in the same direction. We already talked about that with the gear train above. We have a negative train value in that case because the input and output gears rotate in the opposite direction. Here's a tip for figuring out the sign of your train value. You can just count the number of meshes. Okay, so if you have an odd number of meshes, your train value will be negative. If you have an even number of meshes, your train value will be positive. So if I come up here and count the number of meshes in this example gear train that we had 1 mesh here, 2 mesh here, 3 mesh here. So we have 3 meshes. That is an odd number, and that means that our train value will be negative, which is exactly what we saw. Okay, now we can write another equation, and this kind of ties it all together. All right, so this is just relating the speed of the input and output gears through the train value, which is exactly how we arrived at this equation up here. The speed of gear 6 is our last, speed of gear 2 is our first. Okay, now let's talk about compound gear trains. So here is a simple compound gear train, and the definition of a compound gear train is just that it has 2 or more gears attached to the same shaft. So what we had above was also a compound gear train. A compound reverted gear train is one where the input and output gears are also aligned. And so that, you can see, is the case in this example as well. So not only is this a compound gear train, this is a compound reverted gear train. Okay, so I wanted to pause on this for a minute just to say that a compound gear train, like the one that we have up here, can be used to achieve higher gear ratios than one pair of gears. So if I just had a single pair of gears, this could be used to achieve a train value of up to about 10 to 1. With a compound gear train in 2 stages, we can achieve a train value of up to about 100 to 1. So we get a pretty substantial increase in the train value just from adding a second stage in the gear train. Okay, so as it says, having a compound reverted gear train requires the distances between the shafts to be the same for both gear trains. So for this example, let's label our gears. We have 2, 3, 4, and 5 here. And for these input and output shafts to be aligned, we need the distance from the center of gear 2 to the center of gear 3 to be the same as the distance from the center of gear 5 to the center of gear 4. So if we write that out mathematically, we can just say that the half the diameter of 2 plus half the diameter of 3 needs to be equal to half the diameter of 4 plus half the diameter of 5. Now, another note on this compound reverted gear train is that in order for these gears to mesh, the diametral pitch of 2 has to be the same as the diametral pitch of 3, and the diametral pitch of 4 has to be equal to the diametral pitch of 5. You can have different diametral pitches for the separate stages, where gears 2 and 3 are one stage, gears 4 and 5 are one stage. But in order for gears 2 and 3 to mesh together, again, they have to have the same size and spacing of gear teeth in order for them to mesh together. And same thing for gears 4 and 5. Now, for an easy design for interchangeability, we would like to have the same diametral pitch in both stages. So let's assume that we do that. Okay, then I can replace the diameters in this equation with a ratio of the number of teeth divided by the diametral pitch, P. So that would look something like N2 over 2 times P plus N3 over 2 times P equals N4 over 2 times P plus N5 over 2 times P. Now we can get rid of the 2p in the denominator of all of these terms by just multiplying through the whole equation by 2p, and then we get this nice simple relationship between the numbers of teeth on gears 2, 3, 4, and 5. It says that the sum of the teeth on the first stage of gears has to be equal to the sum of the number of teeth on the second stage of gears. And writing things in terms of the number of teeth is often convenient. That's just an easy number to obtain or when you're designing gear trains. If you want to know the size of a particular gear, you can just go out and count the number of teeth on it. That's an easy number to obtain. So that is going to be it for this video. I hope that you found it helpful, and I hope that you're looking forward to hearing a little bit more about gear trains. In the next video, we're going to talk about epicyclic gear trains or planetary gear sets, which are kind of fun and funky. And then we will start talking about failure modes of gears. And so I hope you're looking forward to that, and hope to see you there in that next video.